All right, guys, here we're in the third installment of this section, and we're going to talk about interpreting the integral as a rate of change. So part two of the fundamental theorem of calculus states that if function's continuous on a closed interval and capital F is an antiderivative, then the value of the definite integral is just evaluating the antiderivative at the upper and lower limits and subtracting. But suppose the integrand is a derivative itself, like the function you're using in there is f prime, then the integral of f prime is just f of b minus f of a. So it's nothing different. We're just using different notation because if capital F is the antiderivative of f, then f is got to be the antiderivative of f prime. So all we're doing is we're setting up this equation and solving it for f of b. Okay, basically we're going to add f of a to the other side and flip the equation over. Okay, this formula is going to allow us to get all kinds of information about a function when its derivative is known and one of the function values is known. So let's take a peek at an example here. So if f is a differentiable function whose derivative is f prime, and if f of 1 equals 5, we want to find f of 3. So we have a point and we have the derivative, and we're asked now for the value of another point on the original function. Well, based on this formula right here, okay, f of b is equal to f of a plus the integral from a to b of f prime of x dx. Okay, so basically it's like this is where you started, and this is your accumulation, or how much you moved, or change in y. Okay, so if you add those two together, if you take where you start plus how much you changed over that interval, you'll get where you ended up, which would be at f of b. So in this case, it's going to be f of 3 equals f of 1 plus the integral from 1 to 3 of 3x squared plus 4 dx. So f of 1 is 5. That's given. Plus, now here we're going to have to anti-differentiate. The new exponent would be 3 multiplied by 1/3 cancels the 3 that's there. So it's just x cubed. Plus the antiderivative of a constant is that constant times x. And then we're going to evaluate this from 1 to 3. So just be careful here. This evaluating at 3 and 1 and subtracting, it only applies to the antiderivative part. So it's going to be 5 plus, okay, if we plug in 3, you're going to have 27 plus 12 minus the function evaluated at 1, which is 1 plus 4. Okay? So if we simplify all that up, distribute 12 and 27 gives us 39, 1 and 4 gives us 5. We're going to subtract, add 5 to that, and we'll get 39. Okay, so f of 3 equals 39. Okay, so pretty cool stuff there. The next thing we're going to do is take a peek at using a definite integral with motion on a line. So here, this is more of a situation in which we have a context. So the acceleration a of an object moving on a line is given by a of t, which is 10 e to the t meters per second squared. And t is greater than or equal to 0 because it's time in seconds. So here we go. If the initial velocity is 150, what is the velocity at time t? So we can use a definite integral to figure this out. So for part A, v of t is equal to v naught, or v of t naught, plus the integral from t naught to t of v prime of u du. Okay, so v prime is equal to the acceleration function, which is this right there. And also at t equals, or t naught, That's the initial time. So at t equals 0, um, we have v of t equals v of 0. Forgot to write this over here. V of 0 equals 150. That's the initial velocity in this case. So the integral from 0 to t, 10 e to the t dt. So this is going to be 150, that's v of 0, plus 10 times e, well, those should have been u's. I accidentally wrote t's. E to the u evaluated from 0 to t. So 150 plus 10 times e to the t minus 10 e to the 0. Now, e to the 0 is just 1, so if you multiply it by 10, this right here just becomes subtraction by 10. Okay. And then we end up with 140 plus 10 e to the t. Alrighty. So there's that one there, part A. Now for part B, okay, the initial position is at 0 seconds is 0. Then we want to know what's the position at 2. So similar thing here, since velocity is the derivative of position, we can get the position function by doing s of 0 plus the integral from 0 to t of v of t dt. So s of 0 is 0. V of t, actually, we're going to use u here because the velocity function itself is in terms of t. So we're going to use that answer from the previous step. So 140 plus 10 e to the u du. Now this is equal to, well, the 0 would go away. We got to take the antiderivative, which is 140 t plus, or 140 u plus 10 e to the u. We're going to evaluate it at 0 and t. All right, so we're going to end up with 140 t plus 10 e to the t minus the function evaluated at 0. Well, 140 times 0 is 0 plus 10 e to the 0. And so this is going to end up giving us 140 t plus 10 e to the t minus 10. All right. And then all we have to do now is plug in at 2. So s of 2 is going to be 140 times 2 plus 10 e to the 2 minus 10, which 140 times 2 is 280. We can subtract the 10 and we get 270 plus 10 e squared. Again, this is an exact answer. Now, if you needed the decimal value, you could just pump that into your calculator or Desmos and get the decimal equivalent. But also, to answer the question, after 2 seconds, the object is 270 plus 10 e squared meters would be the units. And it's important to include the units on your answer when the problem has context. Okay? So part 2, the fundamental theorem of calculus states that if f is a function that is continuous on the closed interval and capital F is the antiderivative, then the definite integral is just the antiderivative evaluated at b and a and subtracted. Since f is an antiderivative of little f, then little f can be thought of as f prime, or capital F prime. Since the derivative capital F prime is the rate of change of f, we have the following understanding. that the integral from a to b of the rate of change of capital F equals the change in F from a to b. Okay, so really nothing new in this case here, but we're explaining how an integral can be interpreted as the net change. Okay, so let's look at an example here. We have an integral, or interpreting an integral whose integrand is a rate of change. So the population of the US is growing at a rate of p prime, which is given there. Million people per year. We have some units where t is the number of years since 2020. Part A, we want to find the definite integral from 0 to 5 of p prime of t. So using the fundamental theorem of calculus, we can do this. So part A, the integral from 0 to 5 of 2.867 times 1.005 t dt is equal to, well, we have that constant there, so we can leave that there. And this integrand is just the form a to the t. And we know that the integral of a to the t is itself times 1 over natural log of the base. So here we would have 1.005 t over natural log of 1.005. Now, obviously, you can't cancel those 1.005s because one's being raised to the t power and the other one is inside the natural log. We're going to plug in 5 and 0. So 2.867 times 1.005 to the 5th over natural log 1.005 minus 1.005 to the 0 over natural log 1.005. All right. Anything to the 0 power except 0 itself is equal to 1. So we'd have 2.867 times 1.005 to the 5th minus 1 all over natural log of 1.005. Now, dumping that into a calculator, you get approximately 14.515. Now, that's the answer, the numerical answer. All right, part B asks us to interpret p prime of t in the context of the problem. Now, since p prime represents the rate of change in millions with respect to time, the definite integral from 0 to 5 is going to be the projected change in population in millions of the United States from t equals 0, which is 2020, to t equals 5, which is 2025. So for part B, I'm just going to type here. This is 14.515 is the projected change in population in millions of the US from t equals 0, 2020, to t equals 5, which is 2025. All right. That's one way to interpret it. Notice we have a couple things going on here. We have the answer, which is 14.515, interpreted in context with the units, and the interval for the definite integral is included there, saying that not only is 14.515 the projected change in population, but we're saying when that change is going to occur over the interval 2020 to 2025. So part C says the population of the US is approximately 336 million people in 2020. What's the projected population in 2025? So basically, all right, for part C, we're asked for P of 5. All right. Well, we know from the previous problems that that is the initial population given plus the change in population over the interval that we're looking at. We know that the initial population in terms of millions was 336 plus the change in population, which we actually figured out in part A, is 14.515. So that's 30 or 350.515 million people. Now, if it asks us to report the answer in to the nearest million, we could say 351 million people, and that's the projected population in 2025 for the US. All right, guys, that's it for this one. Hope that was helpful to you. Take care.